Hello everyone, it's September 28th. Alright, it's a bit late, but let's do this. Oh, we got an easier thing. Oh, and then we kind of want to redo this one more time. Yeah, I'll redo this one more time. Alright, perfect. Let's solve this and do the other one more time. Sort array by parity. Given array, move all even at the beginning, followed by all the odd. Return any array that satisfies this. Okay. We can make it inline, right? Yeah, I think we can do it inline. So inline, I think just swapping, right? We're gonna swap. Right. So we have I here and J here. If at a time we look at I, right? If it's even at the beginning, if it's even, we move. If it's odd, we stop. And then we move here. Wait, hold on. What would be the... No. I think we move this, right? If it's odd, we move. If it's even, we will swap, move this forward, right? If it's still even, we'll swap, move this forward. Yeah, I think that's the way, that's the conventional way to do this. Alright, so we have int I equal to 0, int j equal to nums.length, minus 1. Okay, so while I is smaller than j, if nums j mod 2 is equal to 0, we need a temp. Right, we say temp, go to nums I equal to nums j equal to temp. And we'll hit I or plus plus, right? And then we go back again, else j minus minus. Then we return nums. Right, so if on the right hand side, if I find it's an even, I'll always swap with I, push I forward. And because j never moves, so if it's still, then we'll do it again. Okay, let's try this. Yeah, should be right. Oh wow, I did many different ways. Okay, that's an easy one. Nothing more to say. Okay, that's it. All right, so do this one more time. All right, decode a string. So I read it. Another method that we can do is go from right to left. All right, so basically we're gonna decode this to compute the total length, right? So now we have the total length. Now when we have the total length, then we go from right to left, and every time we go at the right, we'll check, right? Because what we want is K, the kth letter. So on the right hand side, so the first thing we do is check if it's a letter, then the count is right, okay? And if the right hand side is a number, then we are going to know the current. Yeah, if right hand side is a, hold on, let me just do this. Don't say it. So we will get it out, right? We'll get it out. So I have leet, and then leet, and then code, and then we have leet, code, leet, code. All right. So we in total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 times 3 equals 36. Right. So we start from here, which is 36. Now we start from here, lead to code 3. So we start from here. It's 36. Okay. Then we can know right. It's 36. Then it's larger than 10. So I need to reduce it by divide by 3. Right? So now we have 12. Okay? And then 12, and then we'll end at this position, right? 12. So say it's 12. Yeah, because we can divide, because it's 36 is too much, right? Which means it definitely is not going to be in this range, in the multiplier range. So it has to be in the previous range, and the previous range is 12, right? It's 12, and then we check this not equal to 12, 11, 10. Boom, we found it, right? So if we never found it, if we still haven't found it, and then we got here, then that means it's not in this repeat. It's going to be in somewhere previously, right? It's going to be somewhere previously. Yeah, I think this is right. Because if it is inside a repeat, yeah, if it's inside a repeat, then we can always go backwards, right? If it's inside a repeat, we can always go backwards. It's only when it's not in a repeat then we cannot go backwards. Hold on, is that right? We are inside 10, and this extends all the way to 36, right? Extends all the way to 36. The question is 36. Yeah, it's not beyond 36, right? It's not beyond 36, which means it's within the current. It's within the current. So if it's within the current, that means it must be within the repeat, right? It must be within the repeat. Now, what if the repeat is smaller? That's a good question. What if the repeat is not 12, but the repeat, let's say, is 9, and you're looking for the 10th one? I guess I haven't fully understood that. Oh, plus you can't do it with this. This is not gonna work. Yeah, this is not gonna work. You're gonna keep adding to it. It's gonna be a gigantic number. Python can do it. I don't think it's no. Yeah, this is not gonna work. But I kind of, let me check one more time. Yeah, we get the size, right? Oh, we'll need to do mod. We need to do mod at the beginning. Because the final size is gonna be the final size, right? The final size is gonna be the final size. And then we'll mod it. And we tell me that where it should be, right? And then, yeah, so we're reducing the k. Yeah, we're reducing the k. So we have the size, and then we reduce the k, right? We reduce the k, and then we just basically say we need to find a kth, right? Which is understandable, because if k is too big, then the current size, right? If the current size is smaller, then we'll loop around. Otherwise, yes. So k, we do that, and then we check on s, and if k is equal to 0, which means we actually need to fit the entire s, we'll return that. Otherwise, size or minus equal 1, yes. Right, yes, size or minus equal 1. Oh, we go all the way down when k equal to 0. Oh, okay. Yeah, but I don't think this one is valid, because the size can get huge, right? Size can get huge. So I think the other method is better. The one that you just count from the front, right? You count from front. So you have the k. Again, we're reducing the k, right? So we start from front, go until we, oh, that's exactly the same, right? You start from k, you start from the front, and you keep going until the value becomes larger than k, right? Until the value becomes larger than k. And then you do a mod, right? Then you do a mod. Then you can your basic selling. You're basically saying that it's going to be the mod, right? It's going to be the mod. So the previous repeat, and then you start from the front again, and from front again. So you keep doing that until you hit k equal to 0, and that's the 1. Yeah, I think that's the solution we have, right? This is the recursion, so we keep going from the front, right? We just keep adding. If it's larger than if the current total larger than the position, then we'll do this, right? We'll do this, and then we'll solve again. If it's smaller, not really. Yeah, if it's smaller, then we do it again, right? We just keep adding, right? If it's smaller, then we keep adding, and if it's this, we just keep adding, and then we say when it hits, right? This is when it hits. But I think I can modify this. I think there is another solution out there, right? Hold a second. So we can do that. Actually no, because when r becomes 0, right? When r becomes 0, I can say that r becomes 0. When r becomes 0, which means position and land current rep, right? Current rep. I think I can say r equal to 0, right? If r equal to 0, I think I can just return s.char at I. Not really. Not really. I think it's I minus 1. Right? If r is 0. Otherwise, it'll solve r. Okay. And then else, we just keep doing this. Okay, would this one work? They only have limited test cases for this. Nope. Stack Overflow. So we're saying it never reaches 0. That's interesting. If line current total is larger or equal to position, then we'll find a new position, right? And then once I find a new position, which is R, then but the R is never 0. Yeah, it will never be 0 because you're always going above. You're always going above the land total, right? Current land total. So every time you just add more. If it covers up, it will do R, right? If it doesn't cover up, yeah, I think this one is still needed. This is still needed. This is when you add the current S, you add it to the position. But this probably can make it, I was going to say it's make it faster, but I don't think it actually made it faster. Huh. Interesting. I minus 1 is... Oh, yeah, you cannot do I minus 1. Ah, so it has to be the original solution. It cannot be I minus 1. It has to go for the current length. Yeah, so whenever... Yeah, because what you want is the position, right? That's what you want. You want is the position. And if r is equal to 0, right, that means the position is the current length. So you return current length. You don't know. Yeah, that's right. Okay, so yeah, that's fine. That's fine. So that's not an easy problem. All right, we'll go back to JavaScript. So the way I do it is I'll check obj object.keys .length. That's how I check whether it's right or not. I don't know. Yeah, that's how I check.
Oh.
Yeah, because I don't really know there's another way to check. what's JSON parse? Stringify. Oh, that's good. Using loop. Oh, what's this? Oh, wow. Gives it the same thing, right? Yeah, I like this. Plain old JavaScript. Pojo. Huh. All right. Oh. Minimum cost. Oh, we go back to cancellation. Oh, we go back. I think that's it. That's all the things. Do you still remember this? Yeah, let's not read this. Just kind of, I don't remember. Min cost to connect all the points. What was this? Minimum spanning tree. Oh, we're saying we're gonna use prims. Yeah, that's prim. The other one is Kruskal. This is Kruskal, right? This is a Kruskal. This is Kruskal. Union find Kruskal. Union find Kruskal. Yes. Oh, this one is, I don't know if this is a good. I did a left to right and right to left. What is this one? I think also I need to revisit. Huh. All right, let's revisit this one. Prim. What's prim? So remember, the prim's algorithm is you start from anyone, right? And you connect to the one that has the least distance. Okay. And then what? And then no, you find one and you have all your next ones, right? And you connect to the one with the least distance, right? And once you make the connection, right? Once you make the connection, then the next step is should be the minimum that can reach both, right? So we go through all the ones. And how do I make change to the ones that connected previously? Yeah, I think this is what I got stuck last time, but I think Prim's algorithm has a smart way to handle this. Well, the remaining, right? The remaining that can all be connected to. I forgot. How do we get? Yeah, I picked this, and then I have these, right? So I can pick this. Now in the remaining, Prim's. I forgot. How'd you implement this? Yes, the edge connected. Everyone is 7, 6, 1, 2, and 7, 8. How do you find these? Right, and you can update. Oh, you're going through all of them, huh? Yeah, I know it's a heap. Wait, it just traverse through all its edges and store the least weight in the variable called answers. No. You go through all the edges. I mean, we start from this, right? And then we have this, so these are in a queue. So this one pop out, okay? And this one pop out. Oh, this is still in the queue. This one is still in the queue. And you can go here, right? Go here, so you can update it if it have a smaller, right? And then, so now this one's added. This one's already in it, but it's still associated with 8. Now this one's added, it's also 8. Now 2 and 7 is added. 2 is added. And the base is the same, so you can pick whichever one. So I say, okay, I just pick 7. Alright, pick 7. And then from 7 go out. 1 is already handled, so we don't do that. So we'll hit 8 and 6. right? We hit 8 and 6. And then we push it in, now 6 is smaller. Ah, it's like Dijkstra. It is like Dijkstra. Wait, hold on. He just directly, we don't change anything, right? We don't change anything. Because what we want is the minimum weight. Minimum weight, not the minimum weight reaching you. Oh, so this is actually easier than Dijkstra. This is actually easier than Dijkstra. Let me think one more time. So you start from some place, right? And you have all its adjacent. So you pick the smallest one. Everybody else is still in there. Then you go to the new one, right? And then you just, you connect. So each time we're picking the smallest among them all. Smallest edge weight. Then you pick, right? And then you go for the next one. Everybody else is still in there. So every time, I think I know. All right, let's just implement this. Okay, so first of all, we need to point. We need a graph, right? We need a graph. Damn, how the graph is gonna be. You know what? We don't need a graph. We have the graph already. Points is the graph, right? We just need to put whoever's in there. But I need a queue, right? So I need a queue. Q is gonna be 2 values. PQ to new priority queue. Okay. Comparator be a tuple 0. Okay. And then we are going to put, so we want a minimum weight, right? We want a minimum weight and points.length. So we're gonna say int visited equal to new int points.length. Okay, so I visited. Now all we need to do is put 0 in it, right? Put 0 in it. I say pq dot add new int 0 0. Okay, so while pq dot is empty. All right. While it's not empty, right? While it's not empty, now we say int tuple will equal to pq dot poll. Okay, so weight is tuple 0. Index is tuple 1. I would call it I. Right? I. Oh, and visited 0 equal to true. Yeah, let's go boolean. Okay. Right, then we'll say for everybody else, right, for int j equal to 0, j smaller than points, length, j plus plus. Alright, now for each one, if I is not equal to j, we just put it in there, right? We just say pq.add new int. Okay, so wait. So we need a wait. Okay. Int private. No. Private int get wait. I have I, j, points. Okay. And it's gonna be Manhattan, right? Should be return. Might as well. Then I don't have to pass. Let's say this dot points equals points, and when I return math dot avs points I 0 minus points j 0 plus math.avs points I 1 plus points j 1 plus is minus. Okay, so now we can just say get weight ij and j. You just add it, right? Well, if it's not equal to j, oh, I can just say if not visited. If j is not visited, we put it in, and then visited j equal to true. Okay, and every time when you pop out, and each time you visit only one, right? Each time you visit only one. So one Dewey and is everybody's visited. Oh yeah, everybody's visited. Yeah, okay. So we say int res is 0, and then we just say res plus equal to tuple 0. This is not needed, right? And then once we're done, because everybody's visited, so I don't have any more in the PQ. Now return res. So this is Prim's algorithm. We basically add the smallest edge at each time. Smallest edge that is connected to the current intermediate minimum spanning tree at each time. OE log E. Alright, let's see. Is this one correct? I feel like it's easier than the other one. But it's not right. That is very, very interesting. It is not right. Huh. output. I think something gets output too much. So if visited yeah, I think you shouldn't. I think because the way it is going, yeah, somebody gets pushed. Yeah, some edge gets pushed out multiple times. Some node gets pushed out multiple times. So I think we have to do this slightly differently. I think we have to do this. When we get it, then we say if visited I, then we need to continue. Okay. Otherwise, visited I equal to true. And then you just say if j is not visited, then we push j in. Yeah, that's the way to go. Then you will push a lot. Yeah, you can push a lot. Because in the previous one, I did this, and then this one, I had this as well. Visited to visit. Yep, I think in order to make this as fast as we can, I need both. I need another Boolean thing. To visit. Okay. Then to visit 0 equal to true. Okay. So we still do this. And then it's to visit. So we avoid repeated. Right? We avoid repeated here. And then actually visited, we'll do it here. That's bonkers. To visit, right? This is to visit. And then we go in. We say if not visited, we'll visit it, right? And then we add. Then we go to the next one. Then we say if to visit is false, then we put it in, and then we put this as true. Ooh, it's interesting. How? And then we put PQ in it, right? Then pause the next smallest one. Now I check whether it has been visited before. It's not. Wait, why? I feel this logic should be right. Okay. 0, 0. Visit is false. Haven't visited. So now I visited, right? And then result is, and then we can go 0. 2 visit is false, so we don't visit 0 again. But we visit 1. Okay. Then 2 visit. So 2 visit 1 is true. Oh, you go through. Oh, your 2 visits is all true. Oh, that's the problem. Yeah, you put everything in there already. But you have to modify it. Because the next time when you come in, the value will be smaller. Oh, that's why. That's why you don't do it. Oh, I see. Yeah. Makes sense. So this is not necessary. Alright. This is not necessary. You just add a new edge. Yeah. Unless this new edge is bigger than the previous. Otherwise, you just keep adding new edge. Okay. Yeah, you're making things more complicated, man. Prim. So I think prim is actually easier. Okay, it's not as fast. Okay, it's not as fast, but it's definitely easier to implement. 72 test cases. Oh my goodness. 72. Whoa. Really? This is slow. Yeah, this is faster. Because you sort it, and every time you just put a minimum. Right, if it's not minimum, then, if it's already connected, you don't add it. If not, you just keep adding, yeah. And Prim works. So finally, this one gets resolved. Oof. Now I go to candy. Some other time, go to candy. All right, that will be it. I will do this tomorrow, if possible. Adios.